Welcome to the second module of TechMar's Advanced Heat Pump Control Training for Radiant Heating and Cooling Applications. My name is Elizabeth Brown. I am a Technical Support Specialist at TechMar Controls with a background in Mechanical Engineering and Education, and I am your instructor for this course. Previously, in the first module, we introduced an overview of radiant heating and cooling. Now in this module, we're actually going to introduce an overview of heat pumps. Now I know many of you are extremely experienced in this area. There are a lot of students with extensive backgrounds in heat pumps. But as I mentioned earlier, this course was designed to include overviews on all of the system components in a geothermal system design. And the reason we developed the course that way is because each piece is critical to the overall success. So even though I come from a control standpoint, I would be remiss if I didn't speak to the entire system as a whole, because even the best control cannot overcome poor designs. So with that being said, I hope even those of you who have a lot of heat pump experience and a lot of background in this area will still get at least something out of this lesson. And we'll move more into controls as we continue through the rest of this course. We're going to begin today's course with an introduction to heat pumps. Now, since the focus of the course as a whole is on hydronic applications, we will begin to narrow our attention on the water-to-water heat pump. Next, we'll look at heat pump operation in both heating and cooling modes, and here is where we're really focused on strictly the water-to-water heat pump. We'll take a look at the efficiencies for the water-to-water heat pump in both heating and cooling modes. And lastly, we'll start to look at what type of hydronic distribution is best suited for a geothermal heat pump system. Now, most people are familiar with the concept of a heat pump and that it is an application of the refrigeration cycle. And just like a refrigerator, heat pumps are designed to transfer heat from one location to another. So just like the image we have shown on the slide, we are absorbing heat from the geofield, and then the heat pump is able to release that heat to the load. The difference between a heat pump and a refrigerator is that a heat pump is reversible, so it's able to operate in heating and cooling mode, unlike a refrigerator. By moving heat instead of making heat, geothermal systems are able to significantly reduce energy consumption. In fact, Natural Resources Canada states that heat pump systems can reduce heating and cooling costs by up to 65%. Now that's for a geothermal heat pump. Heat pumps still use electricity, but they're able to operate at much higher efficiencies than traditional heating equipment. And we'll take a look at those higher efficiencies later in this presentation. The reason they are able to offer these high efficiencies is because we are transporting heat rather than creating heat like a furnace does when it burns natural gas or propane. There are three main sources of energy for heat pumps. An air source heat pump is one that sources its energy from the air. A water source heat pump sources its energy from the water. And an earth source heat pump sources its energy from the earth. There are four main types of heat pumps used in the industry. We have an air-to-air heat pump where we're using air as the source of our energy, and air is on the distribution side as well. We have a water-to-air heat pump where we are deriving that energy from a geofield, which could be sourced from water or earth. And we have an air distribution side. We have an air-to-water heat pump where we are sourcing our energy from the air, but are using a hydronic distribution system. And lastly, we have a water-to-water heat pump, where we have our geothermal heat exchanger, and the source of the energy could be, again, water or earth, and we have a hydronic distribution system. Now, air source heat pumps have one major challenge, and that is that their operating efficiency is lowest when the demand is highest. So the colder the outside air, the more difficult it is to extract heat from it, but that's also when we have the greatest demand for heat. A geosource heat pump eliminates this problem by using the relatively constant temperature of the Earth as a heat source in winter and a heat sink in the summer. So our Earth temperatures are relatively stable as long as we have a well-designed system that doesn't extract more energy than it should. And so we don't have to worry about efficiencies decreasing when demand is at its highest. Now, gas-powered air source and water source heat pumps are an alternative to traditional electric heat pumps. So we can use natural gas or electricity to operate our heat pump. If we use a gas-powered heat pump rather than an electric heat pump, then the compressor is driven by a gas engine rather than an electric motor. Natural gas-powered heat pumps offer an environmental advantage as well, and that's that we can use natural refrigerants like ammonia and water as opposed to industrial refrigerants. So there are options on the market for which type of heat pump you choose. We're going to be focusing on the water-to-water heat pump, and we'll look at that on the following slide. Now, what is geothermal heating? Well, geothermal heating uses the earth or water as its source for energy, and it takes low temperature heat from the ground and concentrates it using a heat pump for distribution to a load. Typically, we are looking at entering temperatures of about 50 degrees Fahrenheit, and we are able to boost that temperature all the way up to 120 degrees Fahrenheit for our load side demands. So let's look at the cycle we have here. 1, energy from the sun warms the ground. 2, fluid in the heat exchanger piping absorbs heat from the ground. 3, the loop piping carries the heat into the building. And 4, the geothermal heat pump transfers heat to the home. Now there's lots of ways we can refer to geothermal heating. Interchangeably, we can use the terms ground source heat pump, geo-exchange, or earth energy. So if you hear any of those terms, we are referring to the same thing. Now, as we said, geothermal heat pumps are reversible. So we can reject heat into the earth during the cooling mode and extract heat from the earth in heating mode. Now, we've all heard that geothermal heat pumps are extremely efficient. Well, how efficient are they? The heating efficiency of a ground source heat pump is measured by what we call COP, which stands for coefficient of performance. Now, coefficient performance is in heating mode only. We refer to something else when we're talking about the cooling capability of a heat pump, which we'll get to later in this module. So to take a look at the COP of a heat pump, we look at how much energy we are taking from the source. So in this case, I'm able to take in 3 kilowatts of earth energy. I then look at how much energy it takes to operate my heat pump. So here I'm inputting 1 kilowatt of electrical energy. So in total, what I'm getting out of my heat pump is 4 kilowatts. So 3 plus 1, because energy is neither created nor destroyed, I have an output of 4 kilowatts. And my paid input is only 1 kilowatt of electricity. So my COP is expressed as my available output divided by the electrical input. In this case, 4 kilowatts divided by 1 kilowatt, which works out to 400% efficiency. So geothermal systems are extremely efficient. Even high efficiency furnaces can't come anywhere close to this level of efficiency. And that really speaks to the popularity of geothermal heat pumps. So as I said, one of the strong selling points that a geothermal heat pump system has is that it is a single system that can provide cooling in the summer and heating in the winter. Now, how can a single system do that? So let's look at the heat pump cycle in greater detail. On the left-hand side, I have my heat source, and on the right-hand side, I have my heat distribution. So we're going to start at the heat source. Now the heat source for geothermal is earth or water. So I have my tubing buried either in the ground or at the bottom of a lake or pond. And this system is going to be a glycol system to make sure we don't experience any freezing. In the heating season, the glycol mixture is brought to the heat pump unit inside the building, and it passes to the evaporator. At the evaporator, the heat is transferred to the refrigerant inside, which boils to become a low temperature vapor. The vapor is then compressed, which reduces its volume and increases its temperature. So now I have a hot vapor, which passes to my condenser. At the condenser, the hot vapor gives up its heat to the load side water, my hydronic distribution system, and the hot gas then passes to the expansion valve. At the expansion valve, its volume is increased, temperature is decreased, and the cycle starts again. So the 4 steps in the heat pump cycle are evaporate, compress, condense, and expand. And it is this cycle which is able to take the energy from the source, concentrate it, and release it to the heat distribution side. So let's take a look at a greater detail when we are in heating mode. Here's my ground loop. And because we are collecting earth from this source, this is my entering source water temperature, which we will refer to as ESWT. And it passes around the evaporator coil before returning back to the ground loop. The heat that it releases to the evaporator is used to evaporate the refrigerant that is contained within the heat pump cycle. The refrigerant then becomes a low temperature vapor. Now it passes through the reversing valve, and we'll get to the reversing valve and speak about it in greater detail in a couple more slides, but that is what is critical to the reversing operation of a heat pump. And then moves to the compressor. The compressor reduces its volume, which increases its temperature. So coming out of the compressor, we have an extremely hot vapor. The vapor then passes to the condenser, and it releases that heat to the condenser coil. Now what is passing through that coil is the water for the hydronic distribution side. And this is what we call ELWT, entering load water temperature. So the temperature of the water that's coming out of this condenser coil and moving to the buffer tank or the distribution system, the temperature of that is called ELWT, entering load water temperature. Then the refrigerant passes through the expansion valve, where the volume is increased and the temperature decreases before it goes back to the evaporator and the cycle starts again. Now I did mention that heat pumps are reversible, and that reversing valve is key to the reversing operation of a heat pump. So now we're going to look at the role of the reversing valve. The reversing valve is what allows the heat pump to switch from heating mode to cooling mode. It is simply a 24-volt solenoid that is energized by an OB signal. Now normally, what happens is the refrigerant exits the compressor and enters the condenser. So you can see we're taking heat from the ground loop. It's moving into the compressor. We have our very hot vapor leaving the compressor, and it's being directed to the evaporator, where heat is released to the distribution side. When we switch to cooling mode, you can see that the reversing valve has changed positions. Now we are taking the refrigerant from the distribution side, It passes through the compressor, which increases the temperature of the vapor. So it is the reversing valve which will redirect the refrigerant vapor and release the heat either to the geoside or the distribution side, depending on whether we are in heating or cooling mode. Now we'll take a look at the heat pump cycle in cooling mode, which is very similar to the cycle in heating mode, except that the reversing valve has been energized. And now the evaporator and the condenser have traded places. So this used to be the condenser, it is now the evaporator, and the refrigerant is being boiled by the returning load water temperature. So we have the load side, which is passing around the evaporator coil. Exiting the heat pump, we have what we call the ELWT, the entering load water temperature, which will be the chilled water. Now coming back from the distribution side, we have warmer water. And it is this water which is going to be passing around the evaporator and boiling that refrigerant. So now we have refrigerant gas, which is leaving the evaporator, moving over to the compressor. And the compressor will reduce the volume and increase the temperature of the gas, so it is now a very hot vapor. And this vapor passes to the condenser. Now in the heating cycle, this was the evaporator, it is now the condenser. So here, the refrigerant is going to be giving its heat to the fluid that's moving around the condenser coil. And that fluid is the glycol that is in the ground loop. So this ground loop glycol, which we call the ESWT, entering source water temperature, even though it's not actually water, it will be a glycol solution to prevent freezing, passes around the condenser coil and absorbs the heat from that high temperature vapor. And then it's going to distribute that heat into the ground loop and then bring back into the heat pump cooler fluid temperature. Now at this point, once the refrigerant has given up its heat, it's going to be a lower temperature vapor which passes through the expansion valve. At the expansion valve, of course, the volume will increase and the temperature will decrease, and the cycle resumes once more. So very similar operation as the heat cycle. In cooling mode, we just have the reversing valve, which changes the direction of the refrigerant flow, and so the condenser and evaporator effectively change places. So we mentioned the heat pump efficiency when we're in heating before, and we referred to that as the COP, which stands for the coefficient of performance. And here we'll show you how to calculate the coefficient of performance. So as we stated earlier, it is the heating capacity, and that's going to be in BTU per hour, divided by the input electricity in watts, multiplied by a conversion factor. So let's take an example where we have a heat pump that requires 2,000 watts to operate, and the capacity under a certain set of conditions is 28,000 BTU per hour. So in this case, it's 28,000 divided by 2,000 multiplied by 3.413, giving us a COP of 4.1. In percentages, that would be 410% efficiency. So that is not unusual to see those high efficiencies when we're talking about the coefficient of performance. Now, those COP values will change as conditions change, and we'll learn about that more in this presentation. On this slide, we're going to look at how a heat pump's COP, or coefficient of performance, changes along with the entering load water temperature, ELWT, and the entering source water temperature, ESWT. So we can see on this chart that the coefficient of performance is highest when the entering load water temperature is at its lowest. So anything we can do to reduce that entering load water temperature will give us a higher heat pump efficiency. We can also see that there is a difference in the efficiency with regards to the entering source water temperature. So that's the temperature of the fluid that we have coming out of the ground heat exchanger into our heat pump. So we have two examples here, one where the entering source water temperature is 50 degrees and one where the entering source water temperature is 30 degrees. And you can see that the higher of those two gives me a higher heat pump efficiency. So to summarize, the coefficient of performance for a heat pump will be at its maximum when the entering source water temperature is at its highest and when the entering load water temperature is at its lowest. So this shows us that the coefficient of performance is not a steady state number. The efficiency of a heat pump does change. And so when we have the colder outdoor temperatures, you can imagine our entering load temperatures are going to be on the higher end. And you can imagine our entering source water temperatures will decrease as well. So as the seasons change, as the outdoor temperature gets colder, it will have an impact on the efficiency of our heat pump. But then likewise, as temperatures get warmer and entering load water temperatures decrease again, entering source water temperatures will also increase, and we will once again see those higher heat pump efficiencies. When we talk about COP, the goal is to minimize the difference between the entering source water temperature and the entering load water temperature. So we want the ESWT and the ELWT to be as close as possible. You can see that if we have a difference of 20 degrees Fahrenheit, my COP is greater than 6. And as that difference between the ESWT and the ELWT increases, my COP decreases. So the key is to keep those entering load water temperatures as low as possible when we're in heating mode and as high as possible when we're in cooling mode. And vice versa with the entering source water temperatures. We want the highest entering source water temperatures in heating mode and the lowest entering source water temperatures when we're in cooling mode. So a lot of that is going to be the design of the system, the design of the geosystem, and the design of the distribution system. Both of those have to be done while keeping in mind the impact that the water temperatures are going to have on the efficiency of the heat pump. When we're using our heat pump for cooling, we don't refer to efficiency as COP. Instead, we refer to it as EER, which stands for Energy Efficiency Ratio. Now, to look at the example calculation, we're going to assume we have a heat pump that has a cooling capacity under certain conditions of 20,000 BTU per hour. Let's also assume that the required input electricity is 1,000 watts. So the EER is the cooling capacity divided by the input electricity. And in this case, that would be 20,000 divided by 1,000, giving us an EER of 20. So here we are showing how the EER changes with regard to the entering load water temperature and the entering source water temperature. Again, on my bottom axis, I have the ELWT, and I'm showing the EER changes for 3 different entering source water temperatures, 90, 70, and 50. Now, when I'm in cooling mode, what I want for the maximum efficiency is entering source water temperature that's as low as possible. And I also want my entering load water temperature to be as high as possible. So the greater my entering load water temperature is going to be, that will have a positive impact on my EER. Likewise, the lower my ESWT, that will have a positive impact on my EER. So the best combination is a high entering load water temperature and a low entering source water temperature. Now in cooling mode, we're obviously not likely to see ELWTs of 90 degrees Fahrenheit. So we're going to be at this end of the chart more than likely. And if we can keep those entering load water temperatures as high as we can, and if we can get the lowest temperature ESWT, that's where we're going to see those highest efficiencies, the highest EER values. Now we're going to get into the design of the geothermal system in the next module. But let's focus on what we can do on the distribution side in order to lower our entering load water temperatures as much as possible in heating mode and have as high as possible entering load water temperatures in cooling mode. Focusing on the heating, what type of heat emitters will work best with low temperature water? Well, we know that traditional radiators operate at high temperature. Same with traditional baseboard units. So both of those are out from a design perspective in a geothermal system. But what about radiant floors? How are radiant floors typically controlled? And how should they be controlled? We'll look at the operation of the radiant floor in the next few slides to see how we can use that to our advantage in a geothermal system. So here's the typical operation. So our room temperature drops below the differential. At this on point, that is when the thermostat calls for heat. It closes the relay, opens the zone valve, and we start allowing heat into the space. So at this point, heat is being supplied to the tubing. It's not yet radiating to the space. The room temperature continues to drop until a sufficient amount of heat is transferred to the floor. So you can see our room temperature dropped to 66 degrees Fahrenheit. We are now at this point, heat has been supplied to the tubing for a while now. And because of the delay between the heat delivery to the floor and the heat transfer to the air, it caused us to drop further below our differential before we started to feel any heat being radiated to the space. So only when the surface gets warm enough does the room temperature start to rise. So there is a delay here between when the floor starts to radiate heat and when the room temperature will actually start to increase. So now we're at 65 degrees Fahrenheit. Here we are in our cycle. The room temperature is going to start its swing back up. So the floor this whole time continues to be charged with heat while the air temperature rises. So now I'm up to 68 degrees. I can see there is quite a bit of heat moving through my tubing and radiating to my floor surface, which in turn is going to radiate to all the occupants and objects in the space. Now this operation continues until the thermostat is satisfied. So now we've moved back up. Our room temperature is at 70 degrees. The thermostat is satisfied. It opens the relay, which closes the zone valve, and we stop delivering heat to the tubes. Now, does that mean we no longer deliver heat into the space? No, it doesn't, because we have very warm floors here and a high thermal mass, so those floors will continue to deliver heat into the space. So just because the zone valve closed when the thermostat was satisfied doesn't mean we stopped delivering heat to the room. That floor was warm. The high thermal mass was charged with heat and continued to radiate heat into the room. The result is an overshoot. So now the room temperature is at 75 degrees. Occupants are probably complaining that the room is too hot. I thought these radiant floors were supposed to enhance my comfort, but now I'm either too cold or too hot. So these are the complaints we see if radiant floors are operated in this manner. So how can we properly control radiant floors so we don't experience these temperature swings? Well, the ideal operation is not what we just saw, and that was attributed to high temperature water circulating in the tubing. So when we have high temperature water, we are going to see the undershoots and the overshoots. We're going to have complaints about comfort, that the room is too cold, it doesn't stay just right for very long before it's too hot. To avoid that, what we want is to circulate low temperature water. If we are circulating low temperature water, we are not going to see those undershoots and overshoots. So we were just talking about how a heat pump is going to operate at its highest efficiency when the distribution temperatures or the entering load water temperatures are at their lowest. And wouldn't you know it, turns out that radiant floors are actually perfectly suited for low temperature water. That is the ideal way to operate radiant floors so that we don't have the overshoots and undershoots. So radiant installations are perfectly suited for geothermal systems. Heat pumps operate at their highest efficiencies when the entering load water temperature is low in heating mode. And radiant installations also provide optimum comfort when the water temperatures are low as well. So the two really are a perfect pairing. Now Tecmar has developed control features that further optimize this performance, and we'll cover those as we continue in this course. In summary, in this module, we introduced you to heat pumps, the concept behind heat pumps, and we looked at how operation varies if we're in heating mode or in cooling mode through the action of the reversing valve. We looked at heat pump capacity and what the efficiency is, or the COP in heating mode, and the EER in cooling mode is. And lastly, we looked at what type of hydronic distribution system is well suited for a geothermal system design. We eliminated typical radiator and baseboard installations because those require higher water temperatures, and focused on a radiant installation. And it just so happens that radiant systems work best at low water temperatures, and heat pumps offer their highest efficiencies at low water temperatures. While the second module in our course has come to a close, keep in mind if you want more information on any of those topics, or you have any concerns or wish I had covered something in greater detail, please just send me a message and I will happily get back to you as soon as possible. If not the same day, then for sure by the next day. Thanks for joining me. I look forward to hearing from you, and you will be hearing from me in Module 3 later this week. Take care. Bye-bye.